Okay, so in the final video for the topic here, we want to look at some application problems involving exponentials and logs to some extent, but more looking at exponential growth and decay. So exponential functions are functions which lend themselves nicely to application problems because we can model a lot of things with exponential growth or exponential decay. There are a lot of natural phenomena that involve exponential growth and decay, whether that's population growth, whether that's cooling. For example, you leave your cup of tea sitting on the table and the rate at which the temperature decreases, well, the temperature decrease, sorry, not the rate of, can be modelled by an exponential function, etc., etc. So there are a lot of applications we can use here. So we want to have a look at a couple of examples to sort of model that, and then you can have a go. So again, like any application or modelling problem, you can group them into two sort of categories. There are the ones where you are given the exponential equation or formula that models the situation and you then just need to do things with that. That is the simpler one. Or there are the ones where you need to develop the exponential equation yourself. Okay, so we'll have a look at a mixture of those problems. So the first example, we have a single amoeba is placed in a petri dish, and after 1 hour it divides into 2 cells. Every hour, all the cells in the dish split into 2 identical cells. Complete the table below to show the time in hours and the corresponding number of amoebas in the dish. Okay, so when t equals 0, when we're at 0 hours, we have 1 amoeba in the dish. After 1 hour, we know that the cell splits into 2 identical cells, so we have 2 cells in the dish. Okay. After 2 hours, we have each of those 2 cells splits into 2, so we now have 4. After 3 hours, each of those 4 cells splits into 2, so we now have 8. After 4 hours, each of those 8 cells now splits into 2, so we have 16. Find the rule connecting, the rule connecting A and T is exponential. Find the rule. Okay, so if we want to think about what's happening here, we're doubling every time. But we don't want to know how to get from one step to the next. We want to know how do we get from this number straight to this number. How do we get to when t equals 4? What is the number of amoebas? So what we're seeing here is that to get to the number of amoebas after 2 hours, we've taken the initial number and we've multiplied by 2 twice. Okay, so therefore to get to this 4, we've taken the initial number, which is 1, and multiplied it by 2 squared, multiplied it by 2 times. Times 2 times 2 is 2 squared. Here we've done 1 times 2 3 times. Here we've done 1 times 2 4 times. Now obviously because it's 1, we don't really need to worry about the 1. So quite simply, our relationship here, the number of amoebas is equal to 2 to the power of t. Okay, will give us the number of amoebas after t hours. So therefore, if we wanted to know how many amoebas do we have after 10 hours, 2 to the power of 10, whatever that is. Okay, example 2. A biological culture contains 100,000 bacteria at 9 a.m. on Monday. If the culture increases by 8% every hour, at what time, correct to the nearest hour, will the culture first exceed 2.5 million bacteria? Okay, so we're going to need an equation that describes, that relates the time in hours to the number of bacteria. And then we're going to be able to use that equation to answer the question. So it increases by 8% every hour. So we're starting with 100,000 and then we're increasing it by 8%, which is to multiply by 1.08 to get whatever that is. 100,000 times 1.08. So that is 108,000. And then we're going to increase, so this is when t equals 0 at the beginning. This is when t equals 1 after 1 hour. This is when t equals 2. After 2 hours, we're going to multiply by 1.08 again. Or we might think about, instead of having multiplied the previous answer by 1.08, we've multiplied the original answer by 1.08 squared. Okay. So if I take that previous answer and multiply it by 1.08, I get 116,640. Or if I had taken the original amount and multiplied it by 1.08 squared, I should get the same value. Yep. So t equals 3. We're going to take the original 100,000 and multiply it by 1.08 3 times. So therefore the original 100,000 multiplied by 1.08 cubed, which should be the same as taking our previous answer and multiplying it again by 1.08. Okay. So we get 125,971.2 times by 1.08 or times by 1.08 cubed. So generally speaking, we want to be able to say that the number of bacteria, let's call that n, the question didn't give us some answers. Okay, so n is number of bacteria, T equals time in hours, so T is hours after, now remember T equals 0 was 9 a.m. on Monday, hours after 9 a.m. on Monday. So therefore, 9 a.m. on Tuesday would be T equals 24. 10 a.m. on Monday would be T equals 1. Okay, so N, the number of bacteria, is going to be equal to, we had the original 100,000, and then we multiply by 1.08 to the power of T. Okay, so if it's 1 hour, we've taken the original 100,000 multiplied by 1.08 just the once. If it's 10 hours, we've taken the original 100,000 multiplied by 1.08 10 times. If it's 0 hours, original 100,000 multiplied by 1.08 to the 0, which is just 1. So we just get the 100,000. Okay, so there's our equation. So therefore we want to know at what time will there first be more than 2.5 million bacteria. Okay, so therefore we want to know 2.5 million, when n equals 2.5 million, what is T? So we want to solve for T. So let's solve an equation with our CAS. 2.5 million equals 100,000 times 1.08 to the power of T, and we're going to solve that for T. Okay, so T is approximately 41.8. So it asks us to give to the nearest hour. So therefore it will take 42 hours for the culture to first be more than 2.5 million. It'll be exactly 2.5 million after 41.824744, etc. hours. So to the nearest hour, we round up to 42. That'll make sure that it's definitely over 2.5 million. So therefore it will be after 42 hours. Alright, part B. If the culture increases by 2% every 15 minutes, at what time, correct to the nearest hour, will, that should be will the culture first exceed 2.5 million bacteria? Okay, so this time we need to be a bit careful because the increase happens every 15 minutes rather than every hour. So this time I'm going to use a different letter. Let's call still N the number of bacteria. Okay, and this time you can use T in this instance will be number of 15-minute intervals after 9 a.m. Now you can set it up that way and that's an easier equation to set up, but it's going to make solving the equation to the nearest hour harder. Okay, so what we might instead do is think about, alright, if we leave T as the number of hours since 9 a.m. on Monday, then we just need to be a bit careful that, okay, when T equals 0, that's 9 a.m. on Monday. And we know that our bacteria starts out at being 100,000. Then we don't go straight to T equals 1 because that would be an hour. So that would be 4 15-minute breaks. So we would go to T equals T on 4, which would be 15 minutes. Okay? And so that's going to be 100,000 times 1.08. Sorry, not 1.08 anymore. We're increasing by 2%, so 1.02. Okay, and then we could go to T equals T on 2. Okay, so so this is 15 minutes. This is 15 minutes. 3T on 4, so that's 3. That's another 15 minutes, and then we finally get to T equals T. Right, so we essentially want, sorry, it shouldn't be T on 4. So we actually want T equals a quarter, T equals a half, T equals 3/4, T equals 1. Alright, and so each time this will be 100,000 times 1.02 squared. That's 2 15-minute intervals. This will be 100,000 times 1.02 cubed. Okay, this one will be 100,000. What's 100,000? Yep, times 1.02 to the power of 4. Okay, so what you need to think about here is that your time is measured in a slightly different way. So in this case, it's not the time doesn't equal that number there, which was what happened in the previous one. Okay, it actually equals that number there divided by 4. Okay, so if we actually think about, sorry, times by 4. So if we actually think about this, if we thought about, let's see if we can come up with our rule. So n is going to be 100,000 times 1.02, but it's not times to the power of t, it's actually to the power of 4t. So if t equals a quarter, that number up there needs to be 1, 4 times a quarter. If t equals a half, that number up there needs to be 2, which is 4 times a half. If t equals 3/4, that number up there in the power needs to be 3, which is 4 times 3/4. So it has to be 4 times t, because that means that for every 1 hour we've actually done 4 increases of 1.02. So when t equals 1, we've actually multiplied by 1.02 4 times because we've done 4 increases in that 1 hour period. So there's my rule, okay, where I've still got t in hours, but the increase is happening 4 times an hour, so every 15 minutes. So this time we want to work out how many hours will it take for the culture to first exceed 2.5 million bacteria. If we've, instead of doing an 8% increase every hour, we've now done a 2% increase 4 times an hour, which might seem like the same thing, but this is the whole idea of compound interest. The fact that we're compounding the bacteria, we're multiplying more frequently, means that it should happen more quickly. So we're letting n equal 2.5 million, and we want to solve for t, 1.02 to the power of 4t. So I'm going to solve that equation with my CAS. Solving 2.5 million equals 100,000 times 1.02 to the power of 4t. And we want to solve that for t. And we find that t is 40.6. And so again, after how many numbers to the hours to the nearest hour will it first exceed 2.5 million? So making sure we round up, it will exceed 2.5 million after 41 hours. So doing the same percentage increase, technically, but more frequently compounding it, it happens a bit quicker. Okay. Alright, example 3. John invests $1,200 in an account which pays 5% interest for n years. Write down a function to describe the amount A in the account after n years. Okay, so John, the amount in his account will be his original $1,200, and then that's going to be increased by 5% every year for n years. So we're multiplying by 1.05 to increase it by 5%. After 1 year, it'll be power of 1. After 2 years, it'll be power of 2. After 3 years, we'd have multiplied by 1.05 3 times. So after n years, it'll be a power of n. So there's my exponential equation because the unknown is in the power. And now we want to use that equation. How much money is in the account after 10 years? So when n equals 10, 1,200 times 1.05 to the power of 10, 100 times 1.05 to the power of 10. Okay, so it's money, so to the nearest cent, $1,954.67 will be in the account after 10 years. Plot the graph of the function found in A. Okay, so we can use our CAS to plot it, but we can also think a bit logically about what's happening here. We've just found ourselves a point, so that's helpful. We know that it's an exponential function, doesn't matter what the base is. We know that when n equals 0, A equals 1,200, so the y-intercept will be at 1,200. The exponential function's just been dilated, so there's no reflections, translations, anything like that. So it's still going to be this, okay? When n equals 0, so this is now n and this is a. When n equals 0, a is going to be 1,200. It also doesn't make sense in this context to draw anything back here because we can't have negative years. So we're just going to be looking at a graph that does this. We're clearly going to need another point, but we've calculated another point here. When n equals 10, y equals 1954.67. Okay, so we're going to be able to draw a graph very easily without really needing to think about, our CAS. Alright, so let's think about maybe, I don't know, 1,000, 2,000, just to give us a rough sense of scale. So it's going to start at 1,200, okay, and it's going to increase 10 years, it'll be at almost 2,000, so something like that. Now be careful that you don't end up with it looking too linear, because the scale that I'm using here means that it's not particularly curved over this particular interval. So you might want to perhaps be a bit more extreme about it. So what you might want to do instead is, let's make it sort of 1,000, 2,000, 3,000, 4,000, whatever. So let's make it 1,200 here. Let's make 10 kind of there. And then we can give that sense that it's getting bigger and bigger and bigger. So if we made this 10, 1954.67, and made this 0, 1,200. But it's important we think about domain in the context of the problem, okay? So it does not make sense to draw the graph when n is negative, so we're only drawing the graph when n is bigger than or equal to 0. After how many years, will John first have more than $3,000? Okay, so essentially, if we think about our graph, we're looking at, so if this is $3,000 here, we want to know how many years will it take for that to happen. Okay, so we're solving our equation equal to 3,000. So 3,000 equals, what's our equation again? 1,200 times 1.05 to the power of n. So if we solve that for n, 3,000 equals 1,200 times 1.05 to the power of n. Solving that for n. After how many years? Now the implication is after how many years, but it should really say give our answer to the nearest year, okay? And so therefore, and again, we need to make sure that we, in this instance, it makes sense to round up. If we were to get 18.2, for example, if we rounded down to 18 years, he wouldn't have more than $3,000 if we rounded down. So it's important that you're a bit careful about how you round here in making sure that it actually answers the question. After how many years, whole number of years, will he first have more than 3,000? It happens exactly at 18.780235, etc. years. So if we round up to 19 years, so I'm just going to write my answer here though, so n is approximately 18.78, and so therefore it will happen, he'll first have more than $3,000 after 19 years. Okay, example 4. A radioactive substance of mass m grams decays according to the law m equals 250 e to the power of negative 0.0003 t. Okay, so here we've been given the equation. So find, t is the time in years, find the original mass of the substance. Okay, so we want to find m when t equals 0. Okay, so m will be equal to 250 e to the negative 0.0003 times 0. So that's going to be 250 times e to the 0, which is just going to be 250 grams. You probably don't need to do any working out to do that. If you let t equal 0, that whole thing is 1, and you're just going to get this number here will give you your initial amount. You might also think about defining functions in these kind of problems if you're going to do a lot of things with the CAS. So you might have defined your function m of t equals 250 times e, make sure you use the proper e, to the power of negative, 0.0003, make sure I put enough zeros, yep, times t, to find your function, and then, doing things with that, m of 0, letting t equal 0 is very easy. Find when the substance will be at half its original mass. This is called the half-life of the substance. So the half-life of a substance is the amount of time it takes for the volume or the mass to reduce by half. Okay, so we want to find t this time. We want to find t when m is equal to half of 250, so 125 grams. So again, subbing in m equals 125 to our equation, 250 e to the negative 0.0003t. I'm going to solve that for t. So if I've defined my function, that's nice and easy. I can solve m of t equal to 125 for t. Okay, but you can also type in the equation. That's fine as well. So t is going to be 2310.49. Again, let's go to the nearest year. Sorry, the question should specify the rounding. Now this is an interesting one actually, because technically if I round this to the nearest year, it is going to be 2,310 years. It won't quite be at half its mass, but if it tells you to round to the nearest year, you round to the nearest year, okay? It doesn't technically say when will the substance be at less than half of its original mass, in which case I would need to round up to 2,311 years. It just tells me when will it be. So it'll still be very close to half its mass. In fact, we can work it out if we were to round it to m of 2310. It's very close. For all intents and purposes, it's 125 grams. Okay. If it specifically said when will it first be less than 125 grams, you need to be a bit careful. So therefore, it's going to be after 2,310 years, which is that number to the nearest year. Okay, example 5. A number of people living in Boomerville at any time, t years after the first settlers arrived, can be modelled by this equation. Now this notation really confuses students, I find. They use this p0 rather than using a different letter. Now if they wanted, they could have set this up as being a times e to the kt, and the question in part A is find a. The reason that they don't call that something different, they call that p0, is because that's going to be the value of p when t equals 0. Because if you let t equal 0, this becomes 1, and that, therefore, is your initial p, which is why they're calling it p0, p when t equals 0, rather than a different letter. Okay, so please don't be thrown by that. You can, if you don't like it, just call it something else and find the value of a. But the point is that number in the front there is the value of p when t equals 0. Okay. Suppose that 500 settlers arrived on January 1, 1850, and by January 1, 1860, there were 675 people. Okay, so t is measured in years after the first settlers arrived. It tells us that the first settlers arrived at this date. Okay, so that date is t equals 0, which makes this date t equals 10. Okay. So we've got some information here. Find the value of p0, so that is the value of p when t equals 0, okay? But if you don't like that, we can still substitute the information in. So we know that 500 settlers arrived when t equals 0, okay? So we know when t equals 0, p equals 500. If you understand the notation, that immediately tells you that p0 is equal to 500, but I'll show you why. So if I let p equal 500 in the equation, 500 equals p0 times e to the k times 0. So that is p0 times e to the 0. And e to the 0 is just 1. And so therefore p0 equals 500. Okay, which is why we've called it p0, because it is the value of p when t equals 0. Okay, so p0 is 500. So therefore my equation is 500 e to the kt. We will now want to find the value of k correct to 2 decimal places, and that is using our second bit of information, which is when t equals 10, p equals 675. So 675 equals 500 times e to the 10k, dividing 675 by 500, is 27 on 20. And converting to a log, 10k equals log base e of 27 on 20, or 675 on 500. It's just a simplified fraction. And then therefore k is 1 on 10 times log e of 27 on 20. The question tells me I can give that to 2 decimal places. So you might have instead solved an equation. Okay, so you might have used your CAS to solve 675 equals 500, so I didn't actually need to do that solving manually, making sure you use the proper E Sorry, I got trapped out of the power. So 10 times k. If we solve that for k, if you press exactly, it'll give you an answer with a base of e, which is actually what we've calculated there. It writes the 10 on the denominator there, and it's also got negative log e with the fraction upside down, but still the same thing as what we found by hand. So Control Enter to get k corrected to decimal places. K is approximately 0.03. Okay, according to this model, what will the population of Boomerville be on January 1, 1900? So if January 1, 1850 was t equals 0, January 1, 1900 is t equals 50. Okay, so our equation is 500 e to the kt, where k is 0.03. Okay. Now, when you're using your CAS, there's no reason to use that rounded value. Okay, don't type 0.03. Use that nice exact value you've got sitting up there. So we want to know when t equals 50. Okay, so p of 50 is going to be 500 e to the 0.03 times 50. Okay, so you might define a function here, or you just might make sure that you type it in being as precise as you can. So 500 times e to the power of. Now I want to copy that answer, but when I copy that, it's going to bring down that k equals as well, which is a bit annoying. So you might instead prefer to just type the number in, but I would type in all of those digits that you can see there on the screen above to make sure you're keeping it as accurate as you can. Times 50. And so that is going to be, now it's what will the population be? Okay, so the population is number of people, so it can't be 0.1 of a person, and so therefore the population, so this is approximately 2242.02. Okay, so therefore population on Jan 1, 1900 is approximately 2242 people. Okay, so again, I've just rounded to the nearest whole person. It won't have actually reached 2242 at that date. It'll be very nearly almost at that point. So it's just rounding to the nearest year, and again, rounding to the nearest person. And it probably should say that explicitly, really. But again, you've got to think a bit logically. I'm talking about people. I can't have 0.2 of a person. It's got to be rounded to the nearest whole number. Okay, so some application problems for you to work through. When you're working on application problems, you can use your CAS. Please think about how your CAS will help you to be more efficient, making sure you work really accurately. Think about defining functions to make the process of calculating quicker and more efficient.